Hello friends, myself Pranita Afre. Welcome to the next session of Solid State. Today we'll cover the topic called crystal defects. So basically what is a crystal defect? The disorders or irregularities in the arrangement of constituent particles of a solid crystal are called defects or imperfections in the crystal. It means whenever a crystal gets arranged in three-dimensional structure at that time, while the atoms or we'll call the particles, while the particles are getting arranged in three-dimensional structure at that time, depending upon the temperature or pressure, some particles may be lacking in the crystal or some extra particle may get involved in it. It may distort the structure, or sometimes an impurity is added into the crystal. So this gives rise to various kinds of defects in the crystal. So that is what we're going to see in this session, that is crystal defect. So basically there are three types of defects, that are point defects, line defects and plane defects. So in this particular session or in 12th standard you have only point defects to learn. So let us have a look at the point defects. So there are these types of point defects, three types, that is stoichiometric defects, impurity defect and non-stoichiometric defect. Again these three types of defects are again categorized into few subtypes. So stoichiometric defects are categorized as vacancy defect, self-interstitial defect, Schottky defect and Frankel defect. Impurity defects have the types like substitutional impurity defect and interstitial impurity defect. Non-stoichiometric defect have the types like metal deficiency defect and metal excess defect. So what kind of defect has arisen in the given crystal structure, depending on that, because of what reason the defect has arisen, depending on that it is categorized into these types. Let us see one by one. First we'll go for stoichiometric point defect. It can be defined as the ratio of number of atoms or number of cations and anions of compounds remains the same as represented by its chemical formula. Suppose there is a crystal of NaCl. If we have considered the crystal lattice of NaCl, so of course the three-dimensional structure of that crystal will have the particles of Na plus and Cl minus. So they will be alternatively arranged like Na plus and next will be Cl minus, then Na plus and Cl minus. So this is how alternately they will be arranged in the three-dimensional structure of the crystal. But so in stoichiometric point defect what happens is the ratio of cations and anions, that means in the salt Na and Cl they have 1:1 ratio of the cation and anion. So this ratio will remain constant, 1:1. So there won't be any change in the stoichiometric formula, or we can say the chemical formula before and after the defect. So basically the stoichiometric point defect does not, as I have given you the example of NaCl, but in stoichiometric point defect the anions and cations, the crystals which are formed by two different ions, are not involved. So in such stoichiometric point defect, basically non-ionic particles will be involved, so that even if there is a particle is missing or an extra particle is added, still as all the particles are neutral, they do not have any charge, so there won't be any change in the ratio. Now if we consider here in the vacancy defect, what happens, if we have considered here the vacancy defect, it means now here there's all the atoms which are involved in this specific defect, that is vacancy defect, all the atoms are of same kind. Suppose we have considered a solid of iron, so all the atoms will be of iron. Now when they are arranged in 3D array, so any one of the atom might be lacking in this in the crystal, so this is how the space will be vacant, and such kind of defect is called as the vacancy defect. The next defect is self interstitial defect in elemental solid. Now as the name suggests, it's self-interstitial defect. So it means each extra particle occupies an empty space in the crystal lattice. Now what happens, if you have seen, this is the continuous one dimensional structure of the crystal. This is again the another we can say layer of it. Now in this, what happens, an extra atom gets added. Yes, that extra particle will be of same kind of course as the other particles are, so it will be of same kind, but it will be an extra, so it will disturb the structure a bit. Of course, it will disturb the structure a bit, and hence an extra crystal, or we can say an extra particle, is getting added in it, in the interstitial spaces. So this kind of defect is called as self interstitial defect in the elemental solid. Now as this each extra, there is an extra particle in the same area, in the prior area only, an extra particle is getting added, right? So of course the mass will increase, volume being same, volume will be same, and the mass is increasing, and hence as the mass increases, so the density will also increase. So in self interstitial defect, the density of the material increases. Now the next is self interstitial defect in elemental solid. If we see an elemental solid, so that is the same thing, but here what happens, a particle from it will leave this particle. Suppose if we look at the diagram, so this particle which was present here has left its place and has left a vacancy over there, and that particle has got shifted to the another place, so that is self interstitial. In this, what happens, the vacancy is created, and that particle which was present over here gets shifted to another space in the same crystal lattice, so it changes its position. So if you see overall, no new particle has been added, the particle has shifted its place, but no new particle has been added. That is why that is called as the, so if you see, the mass is not changed, neither the volume, hence the density will not change, the density will be same. Then next is Schottky defect. Now what happens basically in the Schottky defect is, if you see, these are the cations and anions. Now Schottky defect is of course the that involves the ions, Schottky defect. And the next defect which we are going to see, that is a Frankel defect. As we are considering the stoichiometric defect, it means the ratio of cation and anion will be same. So keeping that in mind, if you see at this structure, this was the perfect crystal structure before having the impurity in it, or before having any kind of defect in it. So this orange are the orange circles which are smaller in size are of course cations. Cations are almost smaller in size than the anion, and the gray colored circles are the anions. If you see here, the sign is given positive and negative sign. Of course, that is the thing to remember, that cations will always be smaller than the anions, right? So if you see this perfect crystal, when gets any kind of defect, when specifically it gets Schottky defect, so what happens in Schottky defect is, when here will be the cation, here will be the anion, and here will be the cation. So that is the space for the cation, this is the space for the anion. If you can see, if you can compare both the diagrams, so what happens, a cation and an anion, both are missing at the same time. So cation and anion are missed, or they leave the vacant space at a time. So always there is a defect where the cation and anion will be vanished at the same time. So a pair will be lacking, a pair of cation and anion. So it might be one pair, two pair, three pair, or any number of pairs, but when this defect will arise, so it will be in pair. If cation is missing, then an anion will also be missing. So this is the Schottky defect. The next defect is the Frankel defect. If you see here in the Frankel defect, this is the perfect crystal, and this is the crystal with the Frankel defect. If you see, what we can observe here is this positive place, or this vacancy which was to be for the cation, so that is now left vacant. But where is that cation? It has just changed the proposition, so it has occupied one of the interstitial spaces in the same crystal. So if you see overall, no ion is missing over there. Yes, to a specific place the ion will be missing, but that ion has shifted to the same crystal, taking another position, the interstitial position, of course. So such kind of defect is called as Frankel defect. And if you see here, as all the cations and all the anions are as it is, so there is no change in the ratio of the cation and anion. Same is the case with the Schottky defect. If you see here, a positive ion and a negative ion both are missing, so there is one less positive ion, one less negative ion, but the overall ratio remains the same or remains constant. If we compare the Schottky defect and Frankel defect, this you can see with the help of diagram as well over here. So here a cation is missing and an anion is missing. Both are missing at the same time. While in the Frankel defect, just this cation is changing its position, and that is taking any of the interstitial space in the same crystal, so that the ratio of cation to anion remains the same in both the defects, that is Schottky defect and Frankel defect. If we see the difference, Schottky defect occurs in those ionic crystals where difference in size between cation and anion is small. So the cation and of course cation will be smaller than anion, but this difference in the size won't be much higher, so it will be very small. Then only these both can be missing at the same time. While in the Frankel defect, if you see, the anion is quite large as compared to that of cation. So cation is so small as compared to anion. That is the reason why this cation can be shifted, right, to the interstitial space. In Schottky defect, the ions have high coordination number, while in Frankel defect, the ions have low coordination number. Whichever ions are present, they'll have high coordination number, then they'll show Schottky defect. In Frankel defect, will be seen where the ions have low coordination number. In Schottky defect, both the cations and anions leave the solid crystal, right? As already I've told you, a cation and anion at the same time both will leave the place, hence to maintain the stoichiometry of the formula or of the crystal. And in Frankel defect, only the smaller ion, of course that is the cation, will leave its original lattice side, and whereas the anion will remain at its original lattice side. So as a whole, if you see, it will be neutral, or we can say the stoichiometry will be maintained. In Schottky defect, two atoms will reduce from the crystal, right, a cation and an anion. So of course that will reduce the mass as a whole, volume being constant, and hence if we talk about the density, yes, the density will decrease as the mass is decreasing. In Frankel defect, if you see, just the cation is just changing its position. So if you think about the mass will be same, and of course volume is same, so there won't be any change in density in the Frankel defect. Schottky defect will be seen in the crystals of the salts like NaCl, KCl and silver bromide, while Frankel defect will be seen in the salts like in the crystal of salts like ZnS, AgCl. So these are the difference between the Schottky defect and Frankel defect. Now the next kind of defect, second type of defect, that is impurity defect. As the name suggests, of course there will be some kind of impurity present in the crystal. So as the name suggests, the foreign atoms are present in the crystal lattice. Any foreign atom which is not the part of that crystal, or which is not the part of the particles which make that specific crystal, so such foreign atom will be added into the crystal, which gives it impurity defect. So first case in that is substitutional impurity defect. Substitutional means a particle will be substituted by other foreign particle. So if you see here an example, copper and zinc. So basically this is the structure of the copper. Basically all the atoms, the blue colored atoms are of copper, and just one extra or a foreign atom has replaced one of the copper atoms. That is why this is the substitutional impurity defect. Now the substitutional impurity defect might occur in the crystal having ions, that is cations and anions. If you see here, this is the crystal having Na and Cl, Na plus and Cl minus. If you see here, they are alternately arranged. A place is vacant over here, and that place is of the Na plus, of course, that is missing places of cation, that is Na plus in this case. And if you see over here, what is this? Yes, this is strontium, the ion of strontium with two positive ions. So if you see here in normal NaCl crystal, Na has one positive charge and Cls have one negative charge, of course each Cl. So one plus and one Cl, so that is neutralized. Now if you see here, as this one place is empty and that is of cation. So to compensate, now as the crystal has to maintain its neutral character, it cannot get any positive charge or any negative charge as a whole. So to maintain the neutrality of the crystal, this one positive charge, if it is lacking here, another impurity will be present over here with an extra positive charge, that is Sr2 plus. So as the impurity has an extra positive charge, that is why this Na plus will leave its place to maintain the neutrality of the crystal. So this is how we get a vacancy through the aliovalent impurity. Aliovalent impurity means which has a greater positive charge, or having a different valency than the valency of the ions present in crystal. So this is about the substitutional impurity defect. The next is interstitial impurity defect. If you see where the atoms are arranged, now this will be seen of course in non-ionic compound, as you can see in the diagram. So if you consider, these all are the atoms of iron. If you can consider steel, so steel is made up of iron, and that is of course some percent of carbon is added into it. So that carbon having very small sizes compared to iron atoms, so that will act as an impurity now, and that will present in the interstitial spaces. So that carbon atoms will occupy the interstitial spaces which are present in between the iron atoms. So this is how it imparts a defect, that of course that is purposely imparted to make the steel, but this is what is the defect, where the carbon atoms occupy the interstitial spaces in the array of the iron atoms. So this is what gives rise to the interstitial impurity defect. Next, the third type is the non-stoichiometric point defect, that is just opposite of stoichiometric defect. Here the ratio of number of atoms or the number of cations and anions of the compounds become different from that indicated by its chemical formula. Now as in the stoichiometric defect, the stoichiometry, that is the ratio of cation and anion, remains same, while in non-stoichiometric point defect the ratio of cation and anion is disturbed. If we consider first type, that is metal deficiency defect, as the name suggests, here the metal is deficient in the crystal. You see A plus B minus, A plus B minus, and here A plus is lacking. So of course A plus, that is the positive charge, so that will always be a metal. So as a positive charge or a cation is lacking, that means a metal is lacking over here. So this kind of defect is called as metal deficiency defect, as the metal is missing over here. So if you see, to maintain the neutrality, this positive charge is gained by this cation over here, which gains an extra positive charge to balance the neutrality of the crystal. If we consider, let us see an example, Fe2 plus and O2 minus. Now here, if any of the Fe2 plus is missing, here Fe2 plus is missing, so that will be replaced by the higher cation, of course of the same ion, that is iron. So here if Fe has 2 positive charge, then, and that is lacking anywhere, so a cation, another cation at another place will gain an extra positive charge to to nullify the effect. or to have the neutral character as a whole for that crystal. So now you can this can be represented as the charge is compensated by conversion of the ferrous to ferric ion, that is Fe2 plus gets converted into Fe3 plus by losing an electron. So for every vacancy, for two ferrous ions are converted into the ferric ion, of course, so that will provide two electrons required by the excess oxygen. So of course that will lose an electron and hence will get converted to the higher valency, to the higher positive charge. Next is metal excess defect. As the name suggests, that is a defect due to extra positive charge accompanying the interstitial position. So here in metal excess defect, what happens? All the particles are as it is, of course. All the particles are as it is over there. Just extra cation and an extra electron is added into the interstitial space. So this is what is the metal excess defect. There is an extra metal which is added in the interstitial space, which gives it metal excess defect. Now as the metal has added with one positive charge, so of course an electron has to be added to have the neutral character as a whole for that crystal. Yes, this is very important to have that the crystal should be neutral always. So whenever an extra positive charge is getting added, so an electron will come with it. If a positive charge is lacking, of course the negative charge will also be lacking over there, just to maintain the neutrality. That is the rule of nature. Then this is the next case with metal excess. So the metal can be excess because of addition of extra metal and of course an electron, while it can be due to the effect due to the anion vacancies. Here if an anion is lacking, like Cl minus, so here if you see this crystal is of NaCl, so the Na plus and Cl minus are arranged alternately to make a structure, crystal structure. Now here if this was the place for Cl minus. If Cl minus is lacking, that means an anion is lacking, and at the place of anion there is a vacancy created over there, so that will be replaced by an electron. So there won't be any particle as such, but just to have the crystal as a whole to be neutral, an electron will be present in that vacant space. So that space is called as F center. So when an anion gets replaced by an electron, leaving the place vacant, so that vacant place with that electron is called as the F center. So this is the defect with excess of the metal.